Hello, good day. Welcome to today's lesson. Today we will be looking at the natural cleansing process of the atmosphere. Okay, so firstly we want to look at residence time. Residence time has to do with the amount of time that a contaminant remains in the atmosphere. This is known as residence time. Why do we need to know about the residence time of any particular contaminant, air quality contaminant? Because the residence time gives us an idea of how long it takes for an air contaminant to be removed from the atmosphere. So again, what is the significance of that? So we know that there will be cleansing processes that can happen, and some of them are natural. So if we have an idea of how long it takes for a contaminant to be naturally removed from the atmosphere, it means that we can also tell what the accumulation rate could be if that particular contaminant continues to be added to the atmosphere while contaminants that had already been there, the residence time has not been completed. So that means then that if you have an overabundance of accumulation, it means you can have a rapidly decreasing level of air quality. Hence the reason it's important to know residence time. For example, let's look at residence time for some various air quality contaminants. So here we have nitrogen gas and oxygen in the atmosphere. These are considered major species because the Earth's atmosphere is made up significantly of these two. So what is the residence time for our nitrogen gas? Here we have actually 1 million years it takes for the nitrogen gas to be naturally cleaned from the atmosphere. Now that's a very long time when you think in terms of human years, because I mean the average human lifespan is what now, maybe between 70 to 80 years. All right. Whereas oxygen, it takes 10 years. So there's a significant difference between the two. So just imagine if you have a rapid accumulation of nitrogen where the residence time is 1 million years, you could have a problem where you now have an unnatural imbalance. Next we have another category of tracer species. Now tracer gas are gases which make up less than 1% by volume of the Earth's atmosphere, and so those are gases essentially that do not include the previous two that we just looked at, the nitrogen and the oxygen. Okay, so let's look at a few of these. For example, our carbon dioxide, it takes 15 years for it to be removed from the atmosphere. Methane, 10 years. And then we have some with shorter time periods. Here we have ozone that will take less than 1 year. Nitrogen gases that would take 1 day. Here we have nitric acid, also 1 day. CFCs, notice, 65 years. And then of course nitrogen oxide, 150 years. So notice there, depending on the gas itself, there are various residence times, some very short and some incredibly long, that it can take a couple generations or more for it to be removed from the atmosphere. Here we have some sulfur compounds. All right, so for example, sulfur dioxide, we see takes 40 days. What do we have here? So this one is carbonyl sulfide. This can actually, according to the data we have here, take greater than 30,000 hours. So if you check the calculation, that's 30,000, so it's more than that. The CS2, that's your carbon disulfide, this one can take up more than 180,000 hours to be cleansed from the atmosphere. All right. So these are just a few that you can get familiar with. Okay. Now we have basically two natural methods of cleansing the atmosphere, and we're going to look at each one in turn. We have the deposition of pollutants, and if you recall, when you did the calculations, you would have calculated deposition rates or settling rates. And then we also have the conversion of the pollutants into other forms that can be removed from the atmosphere. All right. So let's look at deposition first. So rain, snow, and dew, so that's essentially moisture, precipitation, etc. This can wash things like smoke, dust, pollen, and gases out of the atmosphere. All right. However, you want to note that particles with diameters less than 2 microns, that's very tiny particles, they are not usually washed out by the rain, but they tend to remain in the atmosphere. All right. So if they remain in the atmosphere, what happens is they would eventually slowly settle and are then removed by impact with trees, rocks, and other surfaces. All right. So the various surfaces might probably allow them to roll off or bounce off, etc. However, bear in mind that these tiny particles could travel for many miles without regard for national boundaries. Okay. So essentially, you want to remember, when it comes to air pollution, and especially when you're talking about things like gases and fine particulate matter, etc., air pollution can now become a global problem. It's no longer the problem for the polluters or those immediately surrounding the polluters, because that those pollutants can travel long distances by winds, wind currents, etc. All right. So it's very important for us to remember that. So these pollutants can be deposited on the Earth's surface due to, firstly, dry deposition and wet deposition. The dry deposition essentially has to do with settling of the particulate matter. The wet deposition is associated with washout or moisture in the atmosphere, such as the rain, snow, dew, etc. All right. So the dry deposition, toxic air contaminants are deposited to the land and water bodies by settling directly out of the air. So how do we calculate deposition rate? For example, remember, you would have done some of this, so you need to know the deposition velocity, and you multiply that by the concentration of the pollution. Okay. The wet deposition, this is the toxic air contaminants. They are deposited to the land and water bodies through precipitation. So, like, for example, during our dry season, or even rainy dry spells during our rainy season, in recent years we've been dealing a lot with Sahara dust layers coming across the island. Usually we would get some relief when rain falls. So this is what they're talking about. Okay. So this here just gives us a little schematic to visualize some of what we have been talking about in terms of dry and wet deposition. So say, for example, this is your source of emission. So you have nitrogen oxides and sulfur dioxide being released into the atmosphere. Some of those particles will be deposited as dry deposition, right? Others, if you recall, not all will be deposited. Finer particles will remain in the atmosphere. Some of that will be converted through chemical reactions in the atmosphere, such as oxidation, interaction with moisture and oxygen in the atmosphere. All right. and some of it will be deposited or washed out of the atmosphere in wet deposition. So this particular one here shows you the chemical conversion that will result in the production of acids to produce acid rain. So this is also part of the washout process. Okay. So just a little note here on deposition velocity. So there are some factors that would affect deposition velocity. How fast the particulates or the contaminant would be deposited. For example, the solubility of the pollutant. So of course that has to do with the very nature of the pollutant and the level of solubility. Alright, the particulate diameter and density. Well, you all should know that already. Alright, because the size of the particle and the weight of the particle will also play a role in the rate of deposition. Of course, the larger it is and the heavier it is, the faster it would settle. Wetness and roughness of surface. So this has to do with friction. For example, if you have a dry, rough surface, when the particles deposit, you have increased friction. Where you have increased friction, the settling velocity will actually be faster. Alright, if it's wet and smooth, it will not settle as quickly. It will just keep moving. Alright, and of course, I'm sure we understand wind speed and turbulence as well will also affect the rate of settling. Alright, so let's move on. Here are some examples of deposition velocity by contaminants. So alright, so I just want to point out a few here. So here we have an example of nitrogen oxide, and you have a very quick settling rate here. Deposition velocity, very quick. Alright, from 0.01 to 0.1. Right, we also have manganese oxide here. Alright, this is the range, so it's really ranges we have. Alright, 0.5 to 5 centimeters per second. Okay, so this one here, beg your pardon, this one here appears to be pretty long. Alright, so we have several of them here for your reference. Okay, now let's look at some other cleansing methods, because if you recall, we said there were two. There's the deposition, and then there's also conversion of the pollutants to other forms. So here we have a few other examples that we can look at. Sulfur dioxide. So we have some stats here. It says the total world emission of sulfur dioxides are about 100 million tons per year. This can be removed from the atmosphere in about 40 days. So that's your residence time. Okay, so here are some examples, two simple examples of how it might be removed. For example, you can have your sulfur dioxide here that will react with the oxygen in the atmosphere and water to produce sulfuric acid. Now if this reacts with lime, ammonia and lime, it can produce ammonium sulfate and calcium sulfate. So that chemical reaction will produce something else. So the sulfur dioxide has been removed. Here we have another example, the sulfur dioxide plus the ammonia, and the calcite of lime to produce sulfites, which can then be oxidized to produce sulfates. Alright, again we have a total conversion here where you no longer have the pure sulfur dioxide. And so this is the ammonium sulfate. Note, this is a good fertilizer, so it's actually not, this conversion is actually quite useful. So here we have another one where we have hydrogen sulfide and the conversion of hydrogen sulfide and the conversion of ammonia. Right? So for example, the total world emission of the hydrogen sulfide is about 300 million tons per year. Again, that is a lot. Major sources are essentially natural, such as volcanoes and biological decay. However, there appears to be no evidence of accumulation. So it's possible that residence time is likely very short. Okay, so how would we, what kind of conversion would we have here? So we have our hydrogen sulfide, which will chemically react with lead oxide and iron oxide. Okay, so these are metal oxides, and they produce an insoluble metal sulfide. Okay, also note that in the lab, the odor that would be associated with the hydrogen sulfide, that can be removed by adding a few tenths of nitrogen oxide, which acts as a catalyst to form sulfuric acid. Okay, now dealing with the ammonia is removed from the atmosphere by reaction with acids or acid forming oxides. So the chemical reaction that will take place in the atmosphere, that would take place with the acids in the atmosphere, such as the acid rain, etc. Here we have some other examples. We have the cleansing processes of fluorides and carbon monoxide. Let's look first at the fluorides. So the hydrogen fluoride and the silicon fluoride, these readily attack a variety of materials and are readily removed from the atmosphere. So essentially what you want to remember here is that you can have a very quick chemical reaction with other materials in the atmosphere to remove the fluorides. Okay, your carbon monoxide, so the carbon monoxide will react with the hydroxyl radicals. What would happen is that this reaction will take place in the upper atmosphere, right? And that will produce carbon dioxide. So that's carbon monoxide. You have a chemical reaction in the upper atmosphere with oxygen, and it produces carbon dioxide. Again, no accumulation, no evidence of accumulation. Carbon, we're looking at carbon dioxide and nitric oxide now. Alright, so the carbon dioxide first. So we know that carbon dioxide plays a role in photosynthesis. So what you have in the process of photosynthesis, so those will be biological and chemical reactions taking place. The carbon dioxide will be absorbed or consumed in this process. Note, the concentration of the carbon dioxide began increasing in the 18th century. Data reported in literature indicate that the increase has accelerated. So we want to make a connection here with other information that we have. This here tells us that during that period, there seemed associated with the increase in carbon dioxide is with the increase in production and productivity associated with industrialization. And with the industrialization, remember, there was an increase in the consumption levels of fossil fuels. So with the combustion of those fossil fuels, we know that a lot of carbon dioxide was released into the atmosphere and has continued to accelerate since then. Cleansing of the nitric oxide. Alright, so this one is pretty straightforward. When the nitric acid is formed, it reacts with the ammonia or lime to produce ammonium nitrate or calcium nitrate. Alright, this one fairly simple. They didn't give you any chemical formulas this time, not really. Okay, so we move on. Alright, so now we're looking at cleansing smoke and hydrocarbons out of the atmosphere. So the smoke can be removed at its source, where you have smoke particles slowly settling as a result of gravitational effects, agglomeration, or rain. What do we mean here? In other words, well, if at the source of the release of the smoke, where you have these larger particulates, if your environmental conditions are such that, of course, we know the larger particulates, gravity will have a greater effect on its settling rate. But then if you also have rain or a lot of moisture and dew in the atmosphere, it will also promote the settling as well. It would also cause some of the particulates to stick together, thereby increasing the density and the size of it. So these are all factors that we know promotes settling rate. Then cleansing of the hydrocarbons. So we have reaction that can take place between the hydrocarbons as they essentially they react with the light energy in the atmosphere. Alright, so we have a photochemical reaction that can take place with some hydrocarbons that are highly reactive to the light energy in the atmosphere. And lastly, in relation to natural cleansing of the atmosphere, you also want to bear in mind that we have sinks that are available. So what do we mean by sinks? A sink is a reservoir that takes up a chemical element or compound from another part of its natural cycle. Okay, so it takes it up, it collects it and keeps it there essentially. For example, we have sulfur dioxide. So we have scavenging chemical reactions, the soil as well as water absorption, and we can have dry deposition. These are all sources, all possible sources of sink. When we talk about the scavenging, for those of you who don't know, the scavenging is referring to a chemical substance that is added to a mixture to remove or deactivate impurities or unwanted products from the atmosphere. Alright, so other sinks, for example, hydrogen sulfide, that can in the atmosphere react with oxygen to produce sulfur dioxide. Let's see, what else do we have? Nitrous oxide, photodissociation, in other words, it's broken down in the atmosphere. Also, it can find sinks in surface water as well as soil absorption. Let's look at another one. Here's ozone. Ozone in the atmosphere can be impacted by reaction with the light energy to cause a conversion. Alright, so it will break down the molecule. Additionally, ozone can be absorbed by some surfaces such as soil and vegetation as well as surface water. Alright, so these are just a few for you to become a little bit familiar with. And at this point, I want to thank you for joining me for today's lesson. If you can please proceed to eClassroom for further instructions.